New question now, question 71. Takeoff distance available is the total distance available for aircraft to take off, including the length of the runway, plus clearway, minus threshold, displaced threshold, plus stopway. So what is takeoff distance available? So let's say let's draw the diagram. This is your runway. Okay. This is the threshold of this runway. Here. Now this runway, at the end of this runway, there will be a stopway where you can bring your aircraft to a stop should you abort your takeoff. And beyond this stopway or in congruence with the stopway, there will also be a clear way. There will be a clear way like this. Okay. There will be a clear way and then there will be a stopway. This is your runway. Now, the distance between the start of your runway to the end of your stopway is called accelerate stop distance available. The length of runway available for your takeoff run or landing run is called takeoff run. It's called takeoff run available. For landing, there will be landing distance available. Now, the length of your runway plus the length of clear way is called takeoff distance available. Takeoff distance available. So runway plus clearway is takeoff distance available. So option A. 72. Descending with constant true airspeed in an ISA condition, calibrated airspeed, what will happen to calibrated airspeed? What will happen to Mach number? So very important, you are descending at true airspeed, at the same constant true airspeed. So let's say this is your Earth and this is your aircraft. You are descending at constant true airspeed. Okay. Now, when you descend to lower altitudes in the atmosphere, what happens to your atmospheric pressure? Atmospheric pressure increases. Atmospheric pressure increases. Now, first, let's look at the case of calibrated airspeed. Your calibrated airspeed is nothing but calibrated airspeed is nothing but an indicated airspeed corrected for position corrected for position and pressure errors, right? Now this calibrated airspeed is nothing but an indirect representation of dynamic pressure. Dynamic pressure. This dynamic pressure is measured by your airspeed indicator. Now this airspeed indicator is your pressure instrument which uses atmospheric pressure for its working, for its operation. Now, what kind of atmospheric pressure it depends on? It depends on dynamic pressure. Now, dynamic pressure is nothing but your total pressure or pitot pressure minus static pressure. Okay. Now, when you go to lower altitudes in the atmosphere, when you fly down to lower altitudes in the atmosphere, what happens to atmospheric pressure? Atmospheric pressure increases in value. When you climb to higher and higher altitudes in the atmosphere, atmospheric pressure value decreases. Now, when you go to higher altitudes, atmospheric pressure value decreases. That means less and less atmospheric pressure will be available for your airspeed indicator to use. If less atmospheric pressure is available, that means the dynamic pressure registered by your aircraft will be less. Okay, and if dynamic pressure registered is less, so the consequence will be the indicated airspeed, the speed indicated to you on your speed instrument will also be lesser and lesser. So when you go to higher altitudes, Because of decreasing atmospheric pressure, the pressure registered by your airspeed indicator also decreases, and as a result, the speed shown to you will also decrease. As opposed to this, when you come down to lower and lower altitudes, when you fly to lower altitudes in the atmosphere, atmospheric pressure goes on increasing. With increase in atmospheric pressure, more and more pressure will be available for your airspeed indicator to use. This more pressure will be registered by your airspeed indicator instrument, and this pressure will be indicated to you in the form of indicated airspeed or calibrated airspeed. So, when you are descending at constant true airspeed to lower altitudes, what will happen to calibrated airspeed? Calibrated airspeed will increase. It will increase. Calibrated airspeed is solely dependent on atmospheric pressure. It does not depend on temperature, humidity, nothing. Only and only atmospheric pressure. So coming down, atmospheric pressure increases. So if you are descending at a constant true airspeed, what will happen? Calibrated airspeed will automatically go on increasing in value. Okay. Now what will happen to Mach number? When you come down to lower altitudes in atmosphere, what happens to temperature? Temperature increases. So let's say you're descending from 5,000 feet where temperature is 10 degrees Celsius to a lower altitude of 2000 feet where temperature is 20 degrees Celsius. Right? Atmospheric temperature will increase as you come down to lower altitudes. So what will happen to local speed of sound? Local speed of sound at 5000 feet will be 39.17 square root of temperature in Kelvin. So 10 degrees Celsius in terms of Kelvin is 283 Kelvin. So square root of 283 into 39.17 is 659 knots. Local speed of sound at 2000 feet will be 39.17 square root of 293. So square root of 293 is 670 knots. Okay. Now let's calculate Mach number. Mach number at 5000 feet will be true airspeed divided by local speed of sound. You're descending at a constant true airspeed of let's say 300 knots. So 300 divided by local speed of sound at 5000 feet, which is 659. So 300 divided by 659 is 0.45. Mach number at 2000 feet, true airspeed 300 divided by speed of sound 670. So 300 divided by 670 is 0.44 or approximately 0.44. So what has happened to Mach number? Mach number has remained more or less it is same 0.45, 0.44. So the correct answer here will be option Charlie. Descending with constant true airspeed in ISA conditions, calibrated airspeed will increase. Mach number will remain more or less same, constant. Next, a clinic. So a clinic line is a line joining places of zero magnetic dip. Now what is magnetic dip? Magnetic dip is the angle between, okay, it is the angle between your vertical component of earth magnetic field divided by horizontal component of the earth magnetic field. Now on this earth, let's consider this is your earth, magnetic magnetic equator is there, and then we have north pole and south pole. Now at magnetic equator, the horizontal component of the earth magnetic field will be maximum. The vertical component of the earth magnetic field will be minimum. So that means the angle between horizontal component and vertical component will be 0 degrees. Okay. When you go to the north pole, vertical component of the earth magnetic field will be maximum. Okay. And horizontal component will be minimum. At equator, we just have this horizontal component. We do not have vertical component. When you go to the North Pole, there will be maximum vertical component and minimum horizontal component. The angle between them will be 90 degrees. So 0 degree here 90 degree at the poles, and midway, anywhere between 0 degree equator and 90 degree pole, the tan theta, the dip angle will be equal to more than 0 degree, less than 90 degree, between 0 degree and 90 degree. So a clinic line is that line with line that joins faces of points of zero dip angle, 0 degree angle. 74. Radio altimeter transmits amplitude modulated continuous wave, frequency modulated continuous wave, phase modulated wave from 4.2 to 4.4. So a radio altimeter will transmit a frequency modulated continuous wave. Okay, so it's a continuous wave. It's not a radio pulse like used in radar. So it's a continuous wave, and the frequency band is super high frequency band starting from 4.2 gigahertz up to 4.4 gigahertz. Okay, so frequency modulated continuous wave 4.2 gigahertz is nothing but 4200 megahertz. So option Bravo. Course is given, task given, winds are given. What is drift, what is heading, and what is ground speed? Task. Now what is the task given to you? 180, course 120. Winds 340 at 50. 50 knots, 340 degree direction. Okay, so check the values. 340 degree direction, 50 knots, course 120, speed 180. Now this gives us a ground speed of 215 knots, 215, a heading of 110, and drift equal to what? So now drift is nothing but the angle between your heading and your track of course. Now over here, heading is 110 and course is 120. So course is more than heading. Now when course or track is more than heading, so the drift is called starboard drift. Okay. So in a starboard drift, we have track or course more than heading of aircraft. So over here, the starboard drift is equal to 10 degree. 10 degree. Okay. Next. Heading 270, task 250. Course is given, speeds are given, winds and drift. So heading 270, task 250. Course 267, ground speed 213. Okay. So ground speed 213, task 250, course 267, heading 270. So this gives us a wind direction of 287, wind speed 39 knots. So 287, 39 knots. Okay. And drift. Now heading is 270, course is 267. So heading is more than course. So when heading is more than course, you get port or left hand side drift. And this port drift value will be equal to 3 degree. 270 minus 267. 77. Track error is 9 degrees starboard. Drift is 4 degrees starboard. Heading is 090. Find track required and track net good. So, so drift is 4 degrees starboard. When drift is starboard, the heading of your aircraft will be less than the track. Okay. So heading is 090 and this is 4 degree. So track will be more than heading 090 plus 4, that is 094 degrees. Okay, this will be your track. Now this track that we are talking about is track made good 094. Now what is track? Just the track required, the original track. So track error 9 degrees starboard. So track error is the angle between track made good, the actual track that you are flying over the ground, and the planned track or original track that you planned for in your flight plan. Okay, so track error is 9 degrees starboard. 9 degrees starboard means your track made good is 9 degree to the right hand side of your planned track. Okay, so your planned track is this. Your track made good is to the 9 degrees right hand side of that. So track made good is what? It's 094. So planned track will be 094 minus 9, which is 085 degrees. So what is track required? 085. What is track made good? It is 094. Option Charlie is the right answer. Going left hand side, values decrease. So that's why we have subtracted. Next. Highest latitude at which sun will rise above the horizon and set every day is 66 degrees. So let's say this is your earth. We have some important latitudes. We have the equatorial latitude 0 degree. We have Tropic of Cancer 23.5 north. We have Tropic of Capricorn 23.5 south. We have Arctic Circle 66.5 north. We have Antarctic Circle 66.5 south. Okay, so now the sun is able to move or can move only between these two latitudes, Tropic of Cancer and Tropic of Capricorn. Okay, beyond this latitudes, Tropic of Cancer and Tropic of Capricorn, the sun cannot go. Okay, so next we have this Arctic Circle. Now let's say the sun is over Tropic of Cancer, 23.5 degree north latitude. When we have sun in the northern hemisphere, we will have summers in the north hemisphere and winters in the south hemisphere. When we have summers in the north hemisphere, all latitudes or all places above this 66.5 degree north latitude will have a continuous 6 months duration daylight. So they won't have night time. Okay, there will be a continuous 6 months daytime. And at the same time, all places or latitudes below 66.5 degrees south will have a 6 month duration of winters. That is 6 months back to back, 6 months of night time. So there won't be any sunrise, no daytime, only darkness. Okay, so that's why 66.5 degree north or 66.5 degrees south is the maximum latitude above at which the sun will rise above the horizon, means you will get daytime. It will set below the horizon, means you will have evening time, okay, or night time. Okay, above that or below that, above those latitude, okay, beyond that latitudes 66.5 north or beyond 66.5 south, towards the south pole, you will have either continuous 6 months daylight or continuous 6 months night time, depending what season is going on. Okay, so 66 degree. Next, accuracy of one of the SSR mode Charlie transponder is what? So accuracy is plus minus 50 feet. Now let's say this is your transponder. This transponder is mode C capability equipped. That means it is able to transmit the pressure altitude of your aircraft to ATC controller. It will directly transmit the pressure altitude of your aircraft to the ATC controller. Okay, so irrespective of the altimeter setting in your altimeter, the transponder is equipped to transmit pressure altitude of your aircraft. Your transponder may be having QNH in its altimeter pressure setting window or QFE. Irrespective of that, the mode C transponder will only transmit the pressure altitude. Okay, altitude or vertical distance with respect to standard pressure setting 1013. Now, whatever this pressure altitude is transmitted to your ATC controller, this pressure altitude is in the form of or is rounded off to the nearest 100 number. To the nearest 100 number. So let's say your aircraft is flying at 7,520 feet. There is another aircraft which is flying at 7,570 feet. So now the transponder equipped with mode C capability will transmit the altitude of this aircraft to ATC in the form of 7,500. So the pressure altitude reported will be pressure altitude 75. Okay, so this 7,520 won't be transmitted. The pressure altitude will transmit the information as in 7,500. So the 20 number is eliminated and the number is rounded off to the nearest whole number, to the nearest 100, 7,500. Now 7,570 will be rounded off to 7,600. Okay, so the next 100, nearest 100. Okay, so the dividing line is 50. Any altitude less than 50 will be rounded off to the previous 100, nearest 100 number. Any altitude more than 50 will be rounded off to the next 100 number. Okay, so the pressure altitude in this case will be equal to 76. Okay, flight level 76, like that. So this is how rounding off is done. So that means whatever altitude is reported altitude to ATC will be accurate within plus minus 50 feet of the actual or true altitude. Okay, plus minus 50 feet of the actual altitude. Right? 50 is the dividing line. Any number more than 50 will be rounded off to the next 100. Less than 50 will be rounded off to the previous 100 number. So that means the accuracy will be plus minus 50 feet. Last question. When in flight, the needle and turn indicator, a ball indicator, is on the left and the ball is on the right. So let's say this is your turn and slip indicator. This is your inclinometer. It's given here that the needle is on the left. The needle is on the left and the ball is on the right. So when needle is on the left, that means aircraft is making a left hand turn. Making a left hand turn. And ball is to the right. That means aircraft is making an uncoordinated left turn, and this uncoordinated turn is nothing but skidding. It's nothing but skidding. Okay. So let's say this is the center of your circle. You want to make a left hand turn. Okay. You want to make a left hand turn. But what happens in a skidding? When you are skidding, your aircraft gets thrown out of the center of the circle like this. Okay, under the influence of centrifugal force, and that's why this ball in the inclinometer gets thrown outside of the center. Okay, instead of, if you are making a coordinated turn, a proper coordinated turn, the ball will remain in the center, in the goal post, under the influence of balance, centripetal and centrifugal forces. But if you are making a skidding turn, the ball will move outside of the turn under the influence of centrifugal force. the outward directed force. Okay, skidding happens because you are not making your turn with sufficient bank angle. Okay, so if you have an insufficient bank angle, your aircraft will skid. If you are flying very fast, your okay, again you will skid. Inadequate rudder pressure is another reason. Okay, inadequate rudder pressure is another reason. So these conditions cater for skidding. So you are turning, if needle is left, so that means your aircraft is turning left and with not enough bank. So you are skidding, that means you are not employing enough bank angle. So third. So this